So, after having recast matrices as lists of vectors, you may well be asking yourself, why in the world do we need yet another way to think about matrices? So, in order to answer this question, we need to relate our new perspective on matrices to linear combinations. So, we're going to start out with an m by n matrix, A, whose columns are v1, v2, down to vn. And we're going to pick an n tuple of numbers, c1, c2, down to cn. If we think back to our discussion on vectors, we can construct a new m-dimensional vector by taking the linear combination of each of these columns. So if we identify the point c1, c2, down to cn with the vector, which we call x, whose entries are c1, c2, down to cn, we can define A multiplied by x to be the linear combination c1 times v1 plus c2 times v2 down to cn times vn. So for example, let's say that we have a matrix A with two three-dimensional columns, -2, 0, 3, and 3, 2, 1, and another vector, x, which has two rows, 2 and 3. The matrix A times the vector x is defined to be the linear combination 2 times the first column plus 3 times the second column. Scaling the first column by 2, we get -4, 0, 6. Scaling the second column by 3, we get 9, 6, and 3. So when we add them together, we'll get 5, 6, 9. So this is not necessarily the most efficient way to perform this multiplication. Note that in each row of the matrix, we multiply the entry in the first column by the first row of the vector x, then multiply the entry in the second column by the second row of the vector x, then add these two numbers together. So this means that we can compute A times x as 2 times -2 plus 3 times 3, 2 times 0 plus 3 times 2, and 2 times 3 plus 3 times 1. This gives us the sum -4 plus 9, 0 plus 6, 6 plus 3, and we come out with 5, 6, and 9. So as another example, compute the product 1, 2, -1, 2, 4, -2, 0, -3, 6, -1, -2, 1 by the four-dimensional vector 3, 1, -1, 1. You should take a second, pause the video, and compute the product. Now that you've had a second to think about this, here's the solution. 1 times 3 is 3, plus 2 times 1 is 2, plus 0 times -1 is 0, plus -1 times 1 is -1. Proceeding in this manner, the second row is 2 times 3 is 6, plus 4 times 1 is 4, plus -3 times -1 is 3, plus -2 times 1 is -2. And in the third row, -1 times 3 is -3, -2 times 1 is -2, 6 times -1 is -1, and 1 times 1. Adding these together, we get 4, 11, and -10. So we close out this lesson with some 3 properties of matrix vector multiplication that will be extremely important in the future. So we start with the matrix A, whose columns are u1, u2, down to un. So this is an m by n matrix, and 2 n-dimensional vectors, v, whose entries are v1, v2, down to vn, and w, whose entries are w1, w2, down to wn. And finally, a scalar, c, which is just a real number. The first property is A multiplied by the 0 vector, which is the vector having all n entries 0, gives us the 0 vector, which is the m-dimensional 0 vector. 2. If I take the matrix A and multiply it by the vector v scaled by c, that's the same as multiplying the vector v by a, then scaling by c. And finally, number 3, if I add my two vectors, v and w together, then multiply by a, that's the same thing as multiplying v by a, multiplying w by a, and adding the two of them together. It's relatively straightforward to demonstrate that each one of these are true. So for the first one, we simply need to recall what the zero vector is and write down our definition. So a multiplied by the zero vector is the linear combination of 0 times u1 plus 0 times u2 plus ... plus 0 times un. Scaling each one of these vectors by 0 gives us the zero vector. That is, each m-dimensional vector has 0 in each of its m entries. When we add those all together, we just get a bunch of zeros. So we get the zero vector not in n dimensions, but in m dimensions. For number 2, we just need to remember multiplying the numbers b and c together, then scaling u by the result, is the same thing as scaling u by the scalar c, then scaling the result of that by b. So now, to show that a multiplied by cv is the same thing as c times a multiplied by v, we simply need to do what's usually called a definition chase. Scaling v by c simply multiplies each of the real numbers, v1, v2 down to vn, by c. When we act on that by the matrix A, we get the linear combination cv1 multiplied by the vector u1 plus cv2 multiplied by the vector u2 plus ... plus cvn multiplied by the vector un. Now, we simply use the associativity to shift our parentheses. Now, if we factor a c out of each term, we get a sum, which is in fact a linear combination. And next we remember that the linear combination is by definition the matrix A multiplied by the matrix V. Now we've shown that A times CV is the same thing as C times AV. Similarly, our third operation is a consequence of the fact that scaling is distributive for vectors. That is, if I take two scalars A and B and a vector u, A plus B multiplied by u is the same thing as AU plus BU. So just as before, we take A multiplied by V plus W and chase our definitions. U1, U2 down to UN multiplied by the vector whose entries are V1 plus W1, V2 plus W2 down to Vn plus Wn. We can write this as a linear combination, V1 plus W1 times U1 plus V2 plus V2 plus W2 U2 plus ... plus Vn plus Wn times Un. Now we use the fact that we can distribute, and now we group the terms with the V's and the W's together. And finally, we recognize that these two sums are the first one, A times V, and the second one, A times W. And that's all we need to do.